Thermogravimetric analysis instrumentation. In thermogravimetric analysis, the determination of temperature at which a material of reproducible and recognizable stoichiometry is produced is facilitated by thermobalance. Now, there are several types of thermobalances available commercially, but the basic instrumental requirements in thermogravimetric analysis are a precision balance, a heating device like furnace, sample cups, temperature and atmosphere control devices, and recorder. Let us see the various components involved in the instrument used in thermogravimetric analysis. First is the weight measurement, which is done by a thermobalance. Weighing mechanism in thermogravimetric analysis is a modification of a single or double pan balance, an electronically self-balancing device, a torsion balance, or a simple spring balance, depending upon the requirement or the type of work to be done. For the preliminary work in the laboratory, a precision torsion balance is easily adopted for use as a thermobalance. The balance should have the following characteristics. It should be simple to operate, it should be accurate, sensitive, and mechanically stable. The balance should be able to respond rapidly to changes in weight. The balance should have an adjustable range of weight change. The balance should cover a wide range of temperature, even up to 2000 degrees centigrade or more. And finally, the heating rate should be linear and reproducible. Almost all the thermobalances that are used are either the null point or the deflection type of instruments. Deflection balances are further categorized into beam type, helical type, cantilever beam type, and torsion wire. In some commercial instruments, a beam of light obstrued by a wave attached to the end of a quartz spring has been used in quartz spring balance. Photoelectric detection was used in that case. Several commercial thermobalances use torque motor, which is a galvanometer with the sample attached to the needle to some null point. Null is detected by a pair of split photocells behind a wave in a light beam. The next requirement in the instrumentation is the heating and temperature measurement. The furnace design and control takes various forms depending on the degree of sophistication of the instrument. The main requirement is that the heating rate should be smooth so that it can maintain either a linear heating program or a fixed temperature. The simplest temperature program is a variable transformer. Other equipments use conventional thermocouples or resistance thermometers situated close to the furnace winding as possible. Platinum and tungsten windings are commonly used. The nichrome windings give a maximum temperature of 1100 degrees centigrade. A platinum rhodium alloy gives up to 1450 degrees centigrade. At least one commercial instrument is capable of reaching to about 1600 degrees centigrade. In the most common programs, the signal from a thermocouple in the furnace is compared electronically against a reference potential, which can be programmed to correspond to a variety of heating modes and heating rates. Size of the furnace is also important. Small furnaces cools very quickly and it is difficult to control linear heating rate. Large furnaces maintain isothermal temperature and are suitable to maintain linear heating rate, but they attain the required temperature very slowly. One of the major problems in thermogravimetric analysis is the measurement of sample temperature. The self-heating during oxidation, the gaseous products produced during heating, and the reaction of the sample with the atmosphere are some important problems which introduce error in temperature measurements. The commonly used rate of heating is 4 to 5 degrees centigrade per minute. Another requirement in the instrumentation are the sample cups. Several shapes of sample cups are used in thermogravimetric analysis depending on the nature of the system investigated. There are four basic designs of sample cups: shallow pan, deep crucible, covered cup, and retort cup. Shallow pans are used when volatile products are produced during heating and it is necessary to allow the gases to diffuse to the surface to escape. These pans are useful in the study of the thermal behavior of polymers. Deep crucibles are used in industrial scale calcinations or surface area studies. Covered cups are used where the studies have to be carried out in self-generated atmosphere. Retort cups are useful in boiling point studies. Next requirement is the atmosphere control. Atmosphere control is extremely important in thermogravimetric analysis because the weight change in the sample is due to the gaseous products formed during sample heating or the reaction of a sample with the balanced atmosphere. The control of atmosphere can be achieved either in the sample or in the balance. In certain kinetic studies where it is necessary to carry out the experiment in a sample generated atmosphere, the regulation is effected by simply covering the sample container with loosely fitted lid. Another way of maintaining the atmosphere is by flushing the whole balance with an inert gas such as argon. Because of the low thermal conductivity and very low density, helium is usually preferred as an inert atmosphere for the study of polymer decompositions and the study of thermal behavior of several other classes of compounds. However, it is necessary to regulate the pressure. The last component of the instrumentation is the recorder. The recording systems can be of the time-based potentiometric strip chart recorders which check the heating rate of furnace for linearity, or they can be XY recorders from which we get curves having plot of weights directly against temperature. And another method can be the normal mode of recording data, which is the percentage mass change against temperature or time.